All right, let's jump right in. Today, we're going to explore the science behind something you literally do every single day, mixing things together. I mean, from your morning coffee to the very air you're breathing, it all comes down to solutes, solvents, and solutions.
Seriously, have you ever thought about that? When you mix up a drink, say some lemonade or maybe an ORS, how come it tastes exactly the same from the first sip to the very last drop? Why isn't it super sweet at one point and then just plain watery the next? Well, the secret is all in how things mix.
And this shows it perfectly. You've basically got two types of mixtures. Over on the left, we've got a uniform mixture. Everything is spread out so evenly you can't even see the sugar anymore. But on the right, that's a non-uniform mixture. It's pretty obvious the sand hasn't really mixed in, it's just sitting at the bottom. Okay, so let's zero in on those perfectly blended, uniform mixtures. In science, we call them solutions. And to really get what's going on, we need to meet the key players.
So, first up, you've got the solute. This is the stuff that gets dissolved. It's the ingredient that seems to kind of disappear, right? You know, like the sugar you stir into your tea or the salt you add to water.
Then you have the solvent. This is the substance that's doing all the work, the one that dissolves the solute. And a lot of the time, especially with drinks, our go-to solvent is just good old water. And when that solute completely dissolves into the solvent, what you're left with is the final product, the solution. That's our perfectly consistent, uniform mixture that we were talking about. So really, it all boils down to this super simple formula. You take a solute, you add a solvent, and boom, you get a solution. It's the basic recipe for tons of things we see and use every single day. Now, what's really cool is what's happening at a microscopic level, something you can't see with your own eyes. Those little solute particles, the yellow ones here, they don't just vanish. They're actually finding all the tiny empty spaces between the solvent particles and just slotting themselves in, spreading out nice and even. But get this, solutions aren't just liquids, not at all. The air you're breathing right now, that's actually a gaseous solution. In this case, nitrogen is the solvent, just because there's so much of it. And the solutes are oxygen, carbon dioxide, and all the other gases mixed in. Wild, right? So that brings up a really good question. If you're stirring salt into a glass of water, can you just keep going forever? Is there a limit to how much you can dissolve? Let's take a look. And this is something you can totally try at home. You start with your water, add a spoon of salt, stir it up, gone. But if you keep adding more and more, you'll eventually hit a wall. A point where the salt just says, nope, I'm done, and starts piling up at the bottom. The water just can't take anymore. And this leads to two important states. On the left, we have an unsaturated solution. See how it's still clear? That means it can still dissolve more stuff. But on the right, that solution is saturated. It's completely full. It's hit its maximum capacity. So let's just lock in those key terms. Unsaturated means there's still room at the end. Saturated means it's fully booked. And the word we use for that maximum amount that can be dissolved, that's solubility. Okay, but what if we start changing the rules of the game? Let's throw in a new variable, temperature. Does making things hotter or colder change how much stuff we can dissolve? Oh, you bet it does. And this is where it gets super fascinating. For most solids, like sugar, if you heat up the water, its solubility goes up. You can dissolve more of it. That's why hot tea dissolves sugar way better than iced tea. But for gases, it's the total opposite. Warming up a liquid actually kicks the gases out, so their solubility goes down. Now, this isn't just some random science fact. It has huge real-world consequences. This is precisely why cold water is so important for fish and other aquatic life. Cold water can hold on to more dissolved oxygen, which is exactly what they need to breathe. It's a matter of survival. All right, so we've got a handle on why things dissolve. But what about the stuff that doesn't dissolve, like that sand and sawdust from earlier? Why does one sink like a rock while the other just bobs on the surface? The secret here is a little thing called density. I mean, it's an observation we've all made, probably since we were kids, right? You throw some sawdust in water, it floats. You throw sand in, it sinks straight to the bottom. What is the fundamental difference between them that causes this? So here's our puzzle again, side by side. Sawdust floats, sand sinks. They're both solids, they're both in water, but they act in completely opposite ways. And the invisible force that explains this whole thing is density. So what exactly is density? Well, the simple way to think about it is how much stuff or mass is packed into a certain amount of space, or volume. It's basically a measure of how crowded the atoms are inside an object.
I love these analogies because they make it so clear. Think of something with high density as being like a totally packed bus at rush hour, or a super thick forest where you can barely walk. And low density? That's like the same bus with only a few people on it, or a wide open forest with trees spread way out. And if you want to get scientific about it, the formula is actually really straightforward. You just take the mass of an object and divide it by its volume. That's it. Density equals mass divided by volume. You've felt this in your own hands for sure. Imagine picking up an iron rod and a wooden stick that are the exact same size. The iron rod feels way, way heavier, doesn't it? That's because it's so much denser. It's got a lot more mass packed into the same amount of space. So, we've seen how these invisible properties like solubility and density explain so much of our everyday world. It kind of makes you wonder, right? What other hidden forces and secret rules are out there shaping everything we see, from a simple glass of water to the entire planet? It's a great reason to stay curious.